Hello and welcome to the course of Software Defined Networking. In today's lecture, I will be talking about the second plane or the second layer of SDN architecture that is known as control plane. The objective of today's lecture is that at the end of this lecture, you would be able to explain the key concepts and the key functions of the SDN control plane. After that, we will shed some light over ITU layered SDN model, which is important to understand. At the end of this lecture, you will also be able to present an overview of OpenDayLight and REST API. Finally, you will be able to compare the centralized and distributed SDN controller architectures. The roadmap for this presentation is that we are going to study the SDN control plane. But before that, we have to review the SDN architecture. After that, we will see how SDN controller is implemented and different type of interfaces like the south and north and also the east and west. After that, we will study OpenDayLight and REST API. And finally, we will see how the cooperation and coordination among different controllers is enabled or is achieved. So first, let us review the SDN architecture. In the previous lecture, we studied about the data plane of the SDN architecture. We studied about the switches, their components, their APIs, their functionalities, etc. Today we are going to focus on the second plane or the second layer, that is the control plane. Here we will be talking about different APIs, different functionalities, SDN controller and things like that. So first let us see the SDN plane architecture, an overview of the SDN control plane architecture. The main point about SDN control layer or plane is that it actually maps application layer services request into specific commands. As you can see, it is like the intermediate layer. So its main functionality is mapping, related to mapping. Mapping between the applications and converting different service requests to commands. And that commands are passed to the data plane switches. That is from one side. From the other side, it supplies applications, different applications running at the application plane with information about the data plane topology and other activities. It is important to remember that control plane or the control layer is implemented as a server, or if there are more than one SDN controller, then they are implemented as a set of servers, and these servers are known as SDN controller. So basically the SDN controller are servers. It could be a single controller or it could be a set of controllers. If it is a set of controller, or in other words set of servers, then the coordination among these different servers or SDN controller is required. Now the basic control plane functions. Here in this figure you can see different functions of the control plane. This figure actually illustrates the functions that are performed by the SDN controller. What are those functions? Some of them are like the shortest path forwarding, as the name indicates. It uses routing information, and that routing information is actually collected from the switches. and based on that collected information, it established the preferred routes towards the destination. That is the shortest path forwarding functionality, and it is one of the key functionality of the control plane. Second is notification manager. As the name indicate, again, it actually receives, it processes, and it forwards uh, different events like alarm notification, like security alarms notifications, or even changes in the stage of the switch, for example, to an application. So basically, what is the main functionality here? It receives, it processes, and it forwards events to an application. And that event could be like alarm notification, something related to the security, something related to the privacy, something related to the state change, and things like that. So it will notify the applications. Another functionality is the security mechanism. And here the focus is on security. Actually, it provides security enforcement between the application and the services. We also have topology manager. It actually builds and maintain switch interconnection topology information. We also have statistic manager, as the name show that it actually collects data on the traffic through the switches. And finally, we have the device manager. It configure the devices, mean the switches, the different parameters of the switches and the different attributes of the switches. And it also manage the flow tables that we have covered in the previous lecture. Okay, all these functions provided by the SDN controller, it can be viewed like an operating system. And in the context of SDN, that is known as Network Operating System, or NOS in short. Like a conventional operating system, uh, this NOS, Network Operating System, it provides essential services, common application APIs, and also an abstraction of the low layer elements. Okay, so just like the traditional operating system, NOS will provide essential services to the applications. It will provide common APIs to the developer, and it will provide an abstraction of the lower layer devices or elements. Actually, the functions that we just introduced here, they enable the developers to define network policies and manage networks without concern for the details of the network device characteristics, mean abstraction. Okay. Later on, we will see some interfaces like the Northbound Interface, which actually provides a uniform means to access the SDN services and perform network management tasks. Beside from that, the Northbound, let me show you this. The Northbound API. It also enables the developer to create software that are independent, and not only independent from the data plane, but also it provide a great extent up to a great extent usability, that this developed software would be able, or it can be used with a variety of SDN controller. So again, let me summarize the concept. The NOS concept is equal to the conventional operating system concept. It provides APIs, it provides essential services, and it hides the internal details of the devices. And that is possible with the help of Northbound APIs. And this API actually provide a uniform means to the application developer and also the network manager to access the SDN services and perform network management tasks. And this interface also enables the developer to create different types of application software that are going to be independent from the data plane. And also it provides a great extent of reusability, or you can say the application would be able to run on different SDN controller or different servers. Now, a number of different initiatives, both commercial and open source, have resulted in the SDN controller implementation. We have studied different functionalities of the SDN controller. Now let us see the implementation efforts by different commercial and open source organizations. The first one in the list is the OpenDayLight. The OpenDayLight is open source platform and it is founded by Cisco and IBM. It can be implemented as a single centralized controller, but it also enable controllers to be distributed. More than one controllers are also able to work and collaborate in a distributed manner. And beside, the second one is known as ONOS. Remember NOS, Network Operating System? We just explained the concept. And open mean freely available, open source. Actually, it is an open source SDN network operating system. And it was developed by a number of carriers like AT&T and NTT, etc. And the best thing about ONOS is that it is supported by Open Network Foundation. Okay, and it is going to be a major factor in the SDN deployment. And it is used as a distributed controller. And it also provides the abstraction, the functionalities that we just covered. The third one is POX. It is also an open source open flow controller, and it is implemented by a number of SDN developers and engineers. Actually, it provides a web-based graphical user interface. And the best thing about POX is that it is written in Python. Beside, we have a beacon. It is also an open source package developed at the University of Stanford, and it was the first controller that make it possible for beginner programmers to work with and create a working environment of SDN where different functionalities can be checked. Okay, so this is like for learning purpose. We also have the Floodlight open source package, and it was developed by Big Switch Networks. At the beginning, its development was based on Beacon, but it has an active community and they have added a large number of features. Now it has both a web-based graphical user interface, which is Java-based, and also it exposes the different functionalities of the controller with the help of the REST API. Or you can say that you can use the REST API. REST API is at the northbound. Here we have the REST API. So the REST API is actually exposed with the help of this Floodlight, or in simple word, you can use the REST API with Floodlight. Beside, we have two others like Rayo and Onyx. The first one is developed by NTT Labs and it is fully developed in Python. The last one actually is a distributed controller, and it was jointly developed by VMware, Google, and NTT. And the downside of this last implementation is that it is commercial. Okay. Well, in the list, I think the most significant controller is the OpenDaylight, and NOS is also an important one. So later on in this lecture, we will study the OpenDayLight architecture in details. Now let us move to some interfaces. The southbound interface. Let me show you again. We have the southbound interface, and the most popular API at this layer is the OpenFlow. This interface, the south one, it provides the logical connection between the SDN controller and the data plane switches. Here it goes. You see, we have the southbound uh, interface shown by this double-headed arrow, and it actually provides a logical connection between the SDN controller. Here we have the SDN controller, and below we have the data plane switches. Okay, so it provides a logical connection between these two layers or these two planes. Some controller products in configuration, they actually support only a single southbound protocol. However, a more flexible approach is to use a southbound abstraction layer. In operating system, you must be familiar with the concept of middleware. So if you want to have a more flexible approach, then you have to use a layer of abstraction, and that layer of abstraction will provide a common interface for the control plane functions, and it will also support multiple southbound APIs. Okay, so that is going to be the beauty of an abstraction layer, to provide flexibility. Okay, the commonly implemented southbound API, as you can see here, is OpenFlow. But beside from OpenFlow, we also have another API which is known as Forces, which stand for Forwarding and Control Element Separation. And we also have another one which is known as OVSDB, which stand for Open vSwitch Database Management Protocol. And finally, we have the third one, which is known as Protocol Obvious Forwarding, or POF. Okay, so these are some of the APIs at the southbound. But the most common one is the OpenFlow. Okay, actually the OVSBD, it is used for, as the name indicate, V for virtual. So it implements virtual switching, and that is interoperable with almost all popular hypervisor, the concept of virtual machine, hypervisors, and things like that. And actually it itself uses the OpenFlow for message forwarding in the control plane for both the virtual and physical ports. Beside, we also have the Forces, and it is developed by IETF, Internet Engineering Task Force, and they have standardized the interface between the control plane and the data plane for Internet Protocol routers, IP-based routers. And the third one, Protocol Oblivious Forwarding, is actually an enhanced version of the OpenFlow. It actually simplify the logic. It make the logic very generic for forwarding the packets. Okay, so forwarding logic has simplified in this POF API. This is the southbound APIs that we just discussed. Beside from south, we have the northbound interfaces, and the northbound interfaces, it actually enables application to access control plane functions and services. And this is possible without needing to know the details of the underlying network switches. Abstraction again. So typically this is viewed as a software API. The northbound interface is viewed as an API rather than a protocol. In the beginning of this course, I shared with you that standardization efforts lack at the northbound interfaces, and there is no widely accepted standard for this interface, although a number of unique APIs have been developed. And these growing number of APIs actually making it complicated to develop SDN applications. So to address this challenge, the Open Network Foundation, they formed the Northbound Interface Working Group. Okay, ONF has established NBI Working Group. NBI stands for Northbound Interface Working Group, NBI. And their objective is to define and standardize a number of broadly useful API for the northbound. Okay, and the most common one is known as a REST. Let us see the northbound interface graphically. This figure actually shows a simplified example of an architecture with multiple level of northbound APIs. You see, we have multiple level of APIs. Why we need these levels? There is a discussion in the NBI working group about these different levels of APIs, but we will not go into the details because some APIs they are further north while some are like close to the controller. You can see this is like a latitude where some of the APIs are close to the controller while other are far away from the controller, but they are close to the applications. If you are interested in the details, you can go to the NBI working group for details about these different APIs that are organized in the form of a latitude. Okay, for us, the important point to understand is that these three APIs, like the base controller, network service, and NBI application APIs. These APIs are clear from their nomenclatures, like the base controller function API. It actually exposes the basic functions of the controller as it is close to the controller. So it will expose the basic functions of the controller and these APIs are normally used by developer to create network services. The second one is network service APIs. These APIs will expose the network services to the north. And then we have the NBI, that is the Northbound Interface Application API. And these expose application related services because it is close to the applications. It is close to the application plane, to the application layer. So it will expose the application related services, and those applications are built on top of the network services. But we will not go into the further details. Okay, so these are three common APIs. Now let us see ITUT model, which is commonly referred by Y.33 and 00. This is actually SDN high-level architecture. It is defined in the ITUT Y.3300. If you can Google it easily on the internet, ITUT Y.33 and 00. This model has three layers, as you can see. And the three layers, or you can say the three planes, are the application, the SDN controller, and the resource layer. The same thing we are studying from the last 4 or 5 weeks. The same three layers. You can see that these applications interact with the SDN controller with the help of API that form an application control interface. Okay, now here the APIs are referred as application control interface. The application make use of an abstracted view of the network resources, and that view is provided by the SDN control layer. Okay, so actually the control layer provides a means to dynamically control the behavior of the network resources, and that must be instructed by the application layers. So SDN is like the intermediate. It is instructed by the application layer, and it manages and control the network resources based on the instruction that it received from the application layer. And this control layer can be viewed as having three sublayers, and those sublayers are application support, uh, orchestration, and abstraction. First, the application support. It provides an API for the SDN applications as it is closest to the application. So it will provide an API for these applications to access the network information. The second sublayer is the orchestration. Orchestration actually provides the automated control and management of these network resources, and also it provides coordination of request from the application layer for network resources. The concept of orchestration is that it makes the automated configuration, management, and coordination of computer resources. Okay, so the second layer of the SDN controller is the orchestration, which actually automate the control and management of network resources, and it also coordinate the request from the application layer for the network resources. And finally, we have the abstraction sublayer, and it actually, as it is close to the data plane, so it will interact with the network resources, and it will also provide an abstraction of the network resources for flexibility purposes. The third layer of the ITUT model is the resource layer, and it consists of interconnected set of data plane forwarding elements, and those forwarding elements are commonly referred by switches, as we know that. And these switches perform the transport and processing of data packets according to the decision made by the SDN controller. We have studied this resource layer in detail in the previous week. Okay, this resource layer also is made from two sublayers, the control support and data transport and processing. And it is very much clear. Control support means it supports programmability of resource layer functions with the help of resource control interface, as it is closest to the controller, so that is why it's a controller support. And finally, we have the responsibility of the forwarding. So for that, we have the second sublayer. There is the data transport and processing, which provide data forwarding and data routing functions. So this design philosophy actually seeks to minimize the complexity and processing burden on the data switches, because we have move the controls from the switches to the SDN controller. So it will actually minimize the complexity and the burden on these switches. Next, we are going to study OpenDayLight. As I just mentioned, we have different solutions available for the implementation of the SDN controller, and one of the most dominant one is the OpenDayLight. OpenDayLight, as I just mentioned, is an open source project, and it is hosted by the Linux Foundation, and it also involves all major networking organizations. And this project actually aims to produce an extensible open source virtual networking platform, and all of them on top of the existing open flow. So the OpenDayLight is to enable the industry participation or the industry partners to come together and to develop core open source modules, but collaboratively. Okay, so this is not going to be um, the property of a single organization. It's actually have a consortia of different organizations, and they come together and work together and collaborate together towards a common open source module. It is important to understand the OpenDayLight and to explain it in details, because it will give you a good idea of the functionalities of a typical SDN controller, because it is actually the implementation of the SDN controller. So it is important to understand. Here is the brief architecture of the OpenDayLight. Several components are there. Some of them are quite familiar, while some of them are going to be something new for us. I will try to explain most of the components of this architecture. The first component is the first thing is that this architecture consists of 5 layers: 1, 2, 3, 4, and 5. Be, Beneath this architecture, at the bottom, we have the switches. We have the data plane. Okay. So first, let us see network applications, orchestration, and services. We already discussed about the application, orchestration, and services, but just to repeat it shortly, it actually control and monitor the network behavior. It actually used the controller to gather network intelligence, run different algorithms, perform different analytics, and then use the controller to orchestrate the new rules. And orchestration mean automatical implementation, configuration, monitoring, etc. Okay, so that is the first component. Then we have at the second layer APIs. OpenDayLight APIs. REST, we already shed some light on the REST. What is new is the OSGI, which is another API. Actually, the OSGI, it stands for Open Service Gateway Initiative, and it is like a set of common interfaces. So OpenDayLight supports the OSGI framework. The OSGI framework is basically used for applications that will run in the same address space as the controller. Mean they are on the same address space, both the controller and also the application, if they are in the same address space. While that is not always the case, in some scenarios it is possible that the application and the controller, they are not in the same address space. They do not run in the same address space. Even they could be on a different machine. For that scenario, you have to use the REST API. So if they are in the same address space, same machine, then OSGI. If they are in the different address space, then you have to use the REST API. Another important component is the controller functions and services. And this is actually the control plane functions and services. We know this is the complete the layer that we have studied here, the SDN controller layer. Here we go. This thing, this thing is actually the controller functions and services. And what are those functions? These are the functions that we just studied. So SDN control plane functions and services, they are defined here. We also have a service abstraction layer, SAL. and it provides, as the name indicates, abstraction. So it will provide a uniform view of the data plane resources. Here we have different resources. So it will provide a layer of abstraction. It will provide a uniform view of the data plane resources. Why? So that the control plane functions here, the control plane functions can be implemented independently of the specific interfaces and specific protocols and specific devices. So that is the basic responsibility of SAL. We also have the southbound interfaces and protocols, and this is not something new. We are already familiar with it. It actually means that it has support for OpenFlow and other standard protocols and vendor specific interfaces. So other protocols are like ONF, IETF, and vendor specific interfaces are also possible. Well, this OpenDayLight, it encompasses both. If you give attention, it is composed of both the control and application plane functionalities. Okay, here we have the application plane functionalities. Actually, you see here we have the northern APIs, and above that API we actually have the applications. So this OpenDayLight architecture contains both the control plane and the application plane functionalities. That is why this OpenDayLight is more than just an SDN controller. Okay, SDN controller is actually this part, but it also has a layer which represent the applications or the services. So this OpenDayLight is more than just the SDN controller implementation. Another aspect of this architecture is that it is not tied to OpenFlow. You can see it also has support for other APIs. Okay, so it is not only tied to the OpenFlow or any other specific southbound interfaces, which means it will provide a greater flexibility in constructing SDN network configuration. And the key element in this is the SAL, which provide an abstraction layer on top of the switches. And this abstraction layer will enable the controller to support multiple protocols on this southbound interface. This was about the OpenDayLight architecture. The next topic is another API, or I would say more than API, and that is known as the REST. REST actually stands for a representational state transfer. It is an architectural style that is used to define APIs on the northbound. And it is actually a standard way of constructing northbound APIs for SDN controller. A REST API, as I just mentioned, is not a protocol, or it is not a language, or there is no well-known established standard available yet. Essentially, it is like an API, or more, you can say that the REST is the REST API actually contains different constraints. Some of the constraints are mentioned here. Or you can say that any API for the northbound of the SDN architecture, they have to follow these restrictions. Okay, so REST architectural style is actually used to define other APIs, and this is now becoming a standard way of constructing northbound APIs for the SDN controller. So it is not actually a protocol, it is not actually a language, or even it is not actually an established standard yet, but it is a standard way, and it essentially defines 6 constraints that an API must follow. Why? Because these constraints are important to be RESTful. So the objective of this constraint is to maximize the scalability and interoperability or independence of the software interactions with the other component. What are these constraints? These constraints are client server, stateless, cache, uniform interface, layered system, and code on demand. Actually, this REST take care of the concept of a web-based access. Means if you are using REST, you are using a web-based access for interaction between the application and the services. Let us see these restrictions in details. The first one is client server. As the name indicate, client server, the interactions between the application and the server is in the client server request response style. If you are familiar with the client server architecture, you would be able to understand this concept. Client make requests, server respond to those requests. So it means that the interaction between the applications and the server must be in the form of request response style. It will actually allow client and server component to evolve independently. Mean one component, either the server or the client, would be able to change without affecting the other component. It also supports the portability of the server-side functions to be to multiple platforms. And then we have the stateless constraint. This is something related with the web, stateful, stateless. So stateless actually mean that each request from the client to a server must contain all necessary information to understand the request, and it cannot take advantage of any stored context on the server. Same is the case from responses from the server side. Any response from the server side will contain all the desired information for the request. In simple words, server does not retain any record of the client state. If the client and server resides on different machine and therefore they communicate with the help of a protocol, that protocol need to be connection oriented. So REST typically run over HTTP protocol, and that protocol is a stateless protocol, and stateless protocol mean you have to retain no information neither on the server side nor on the client side. But we do have support for cache. But to use cache, you need permission. And you are familiar with the concept of the cache. Actually, here in the context of REST, the cache constraint means that the data within a response to a request be implicitly or explicitly labeled as cacheable or non-cacheable. It must be there. If a response is cacheable, then a client cache is given the right to reuse that response for later use. And same is the case for request. So that is, the client is given permission to remember this data because the data is not likely to change on the server side. If it is changed, then we will be in inconsistent state. Therefore, subsequent request, in case if the cache permission is given, then subsequent request for the same data can be handled locally at the client. What is the advantage of this approach? Actually, we are reducing the communication overhead between the client and the server. And we are also reducing the server processing burden. If you have requested for information, you are a client, then you have to store that information in your local cache, and it will minimize the load on the server as well as it will reduce the communication overhead between the client and the server. After that, we have the uniform interface. As the name indicates, this REST give emphasis on the uniform interface between the components. It will enable the controller services to evolve independently. Okay, and it will provide the ability for an SDN controller to to use software components from various vendors in order to implement the controller. If you are using a uniform interface, this will enable the controller services to evolve independently, and it will also provide the ability for an SDN controller provider to use software components from different vendors in order to implement the controller. And then we have the other two, like the layered architecture and the code on demand. So the layered system actually means that a given function is organized in layer. As we saw, many architectures all are organized in layers form. This is the constraint, what the constraints say, that the given functions is organized in layer, and each layer only have direct interaction with the layers immediately above it or immediately below it. Okay, so this is like a fair standard architecture approach for protocol development. Even operating system design, system services design, all follow this approach, the layered approach, and it has some advantages as well. And finally, we have the last constraint for developing API for the northbound, and that is the code on demand. Actually, the REST allow client functionality to be extended by downloading and by executing code in the form of applets or in the form of script. You are familiar with these terms if you have studied the web development courses. This actually simplifies client by reducing the number of features required to be pre-implemented. Okay, so you can download these things if required, and it will also improve the system extendability. These were some restrictions that we need to follow if we are designing an API for the North. Last topic for today lecture is the cooperation and coordination among controller. So we have studied the northbound APIs, the southbound APIs, but what about the east and west APIs? A typical SDN controller will have an east and west interfaces that will enable communication within the SDN controllers or maybe with other networks. To understand the cooperation and coordination, we need to understand the concept of a distributed environment. A key architectural design decision is whether you are using a single controller or more than one controller, SDN controller. So a single centralized controller, or in other words, a single SDN controller, or on the other side, a distributed set of controllers. You have two options. Either you are using a single controller or you are using a set of controllers. If you are using a set of controllers, then those controllers are distributed. Okay. Actually, as we know that the controller job is to control the data plane switches, to instruct the data plane switches. So if you are using a single centralized controller, then a single server will manage all the data plane switches in the network. Okay. However, in larger network setups, in larger organizations, in large enterprises, the deployment of a single controller to manage all network devices would be undesirable, would not be a good practice. A more likely scenario is that the operator of a large organization, large enterprise, large network setup, or a large carrier network, they will divide the whole network into a number of domains, and those domains are non-overlapping, and those domains are commonly referred by SDN Iceland. and they are going to be managed by the distributed controllers. Here are the advantages or the reasons for using more than one controller or for using distributed controller. The first one is scalability. The number of devices in SDN controller can manage is limited. Therefore, a reasonably large network setup may need to deploy multiple SDN controllers. So scalability. Reliability. We know that the use of multiple controllers would avoid the risk of a single point of failure. Privacy. A carrier may choose to implement different policies for privacy in different domains. Okay, for example, an SDN domain may be dedicated to a set of customers who implement their own highly customized policies, requiring that some networking information in this domain should not be disclosed to an external entity. So inside a specific domain, you can specify different types of privacy policies that would be implemented within that domain. And finally, it will it will allow the incremental deployment. As we know that dividing a network into multiple individual domains allow for more flexible incremental deployment. You have 4 domains, and then after some time the requirements have been changed and you want to add another domain. That is going to be a flexible solution, an easy solution. Okay, so these are some of the advantages, or you can say the requirements or the reasons why we need more than one SDN controllers. But what about the cooperation and coordination among controllers? As now we have more than one controllers, so we need them to coordinate and cooperate with one another. Distributed controllers may be allocated in a small area, or maybe they are deployed worldwide. Okay, so in either case, they are distributed, but they are distributed horizontally. What does it mean? It means that each controller control a non-overlapping subset of the data plane switches. It is important to remember that a vertical distributed architecture is also possible, and in that case the controller tasks are distributed to different controllers depending on the criteria. Different criteria such as locality, such as network topology, etc. But for us, the important point is that they are distributed horizontally. So each one is responsible for controlling a non-overlapping subset of the data plane switches. And for that, they need to communicate with one another, mean communicating among the controller. That is the coordination, that is the cooperation. So in a distributed architecture, a protocol, an API, a solution is needed for communication among the controller. Okay, you can use a proprietary protocol for this horizontal communication, although several open and standard protocol would clearly be more beneficial in terms of interoperability and flexibility. Okay, so this is about the cooperation and coordination among controller. If you are using a distributed setup, then and you are using more than one controller, then you need protocol for communication among the controllers. And this was the last topic for this lecture. Thank you so much for attending the lecture. Take care and goodbye.